Welcome to review on Electrochemistry, Chapter 20. Make sure you got a piece of paper and a pencil available. Have your standard reduction potential tables out from the yellow periodic table. Electrochemistry is nothing more than oxidation or reduction. Loss of electrons is oxidation. Gain of electrons is reduction. Loss, ox, gain, red. To be able to know if something is undergoing an oxidation-reduction reaction, you must be able to identify the oxidation states of the reactants in the products. Here are some possible rules. Fluorine is always -1. Oxygen is almost always -1, except in H2O2. I'm sorry, -2, except in H2O2 where it's -1. Hydrogen is +1 with nonmetals, -1 with metals. These, of course, assume that they're combined with something. Good guesses, chlorine, bromine, and iodine are -1 with metals, but of course they're different charges with oxygen in oxyhalogen ions. Group 1's +1, group 2 +2s, and the sum of the charges of a species must add up to whatever that charge is. So if it is something like NaCl, it's neutral. The charge of sodium and the charge of chlorine must sum to 0. If it's SO4 2-, the sum of the sulfurs plus the sum of 4 -2 oxygens must add up to -2. Therefore, sulfur must be +6. Okay? These should be memorized. These must be memorized. Here's an oxidation-reduction reaction. How do I know it is? Well, I can assign oxidation numbers to find out. Monatomic ion, -1. Chromium right here, +3. Both weak animals because they've got the charges next to them. Chlorine right here, alone by itself, 0 charge. Oxygen right here, -2 times 7 is going to add up to -2. There's 2 chromiums. Chromium must be, let's see, -14, -2. It's got to be +6. Notice chromium goes from +6 to +3. It is reduced. Chlorine goes from -1 to 0. It goes up in charge. It's oxidized. If something goes up in charge, it's oxidized. If something goes down in charge, it is reduced. Down, reduced, down and reduced start with consonants. Up and oxidized start with vowels. To balance this, you're going to have to write what are called the half reactions. And we're going to go through the steps to balancing a redox reaction right now. And I'm going to outline 6 different steps that are going to make you do this. 6 different steps that are going to help you do this. I'm going to set aside these half reactions for a second. Write these on a different piece of paper so you can be looking at them at the same time. Here are the rules for balancing redox reactions. First of all, assign oxidation states, which I just did on both sides of the reaction. Second, break it into half reactions, or divide it into half reactions. The oxidation half reaction, the reduction half reaction. To the half reactions themselves. First of all, balance anything except hydrogen and oxygen. Then balance the oxygens by adding H2O. Balance the hydrogens by adding H+, because it's going to be in an acidic solution. Why can you just add H2Os? Well, because it's in a water-based solution. Of course, there's water available. And then add electrons to balance the charge on each half reaction. Multiply the half reactions by numbers as needed to make sure that the electrons cancel out. Then add the half reactions together. Then check. Check to make sure you're balanced for charge. Check to make sure you're balanced for mass. Add OH- ions if it's in basic solution. We're going to set this aside, or right below, as we balance this redox reaction. So, step number 1, assign oxidation states. I did that. +6, -2, -1, +3, 0. Next, divide it into half reactions. I already said that this is the reduced part of the reaction. So here's my reduction half reaction. Here's my oxidation half reaction. Okay? Second, balance everything, or part 3 now, balance everything except for hydrogen and oxygen. 2 needed right there. 2 needed right there. Okay? Now balance the oxygen by adding waters. I'm going to have to add 7 H2Os to this side. Okay? Then add H pluses to balance those out. There's 14 H's here, so I'll need 14 H pluses right here. Then add electrons to make sure that it balances out. Positive 6 total on this side, 2 times positive 3. Positive 14 minus 2 is positive 12 right here, so I will need 6 electrons to make sure that it's positive 6 on this side to match positive 6 on this side. It's negative 2 here. I'm going to need 2 electrons on this side to balance it out. Next, multiply the reactions as needed to make sure that the electrons cancel out. Okay? I'm going to multiply this reaction by 3. Because then I can have 6 chlorides, 3 chlorines, 2 times 3, or 6 electrons. The 6 electrons now cancel with the 6 electrons. And I can do part 5, add the half reactions. So adding these guys together, take all the things on this side, add them together, all the things on this side, add them together. 14H plus Cr2O72 minus plus 6Cl minus, arrow 2Cr positive 3 plus 3Cl2s plus 7H2Os. Check to see if it balanced for charge and mass. Over here on this side, positive 14 minus 2 is positive 12 minus 6 is positive 6 on this side. On this side, positive 6, 0 and 0. Charge is balanced. Check for mass. 14 hydrogens, 14 hydrogens. 2 chromiums, 2 chromiums. 7 oxygens, 7 oxygens. 6 chlorines, 2 times 3, 6 chlorines. It is now balanced. If it was in an basic solution, you would have to add 14 OHs to both sides. These would form waters, and you could cancel some waters over here, and you'd end up with 14 OHs over here. It's not, happens to be in an acidic solution. If you're not good at these steps, you need to practice them. If you don't have these steps memorized, you need to memorize them. You need to memorize them and become good at balancing reactions. You need to become good at balancing those reactions. Okay? Next part, voltaic or galvanic cells. Voltaic or galvanic cells. 2 words mean exactly the same thing. That means a spontaneous redox reaction occurs that has an anode and a cathode, and it passes electrons through it through an external circuit. The anode is where oxidation occurs. The cathode is where reduction occurs. You can remember red cat. You can remember anox and a red cat. Those are the ways to remember oxidation and reduction at the anode and the cathode. So what does a voltaic or a galvanic cell look like? Here's a great picture right here. So on page 857 of Brown-Lummy-Burston, you can see that we've got an anode right here that is losing electrons and becoming a Zn positive 2. Here's the half reaction. We've got a cathode right here, gaining electrons, becoming solid copper. The cathode right here is becoming larger. The anode is being eaten away and becoming aqueous. We are connected by something called a salt bridge. Notice it starts at the anode. The electrons are lost there. The electrons go through the wire to the load, a voltmeter or a light bulb or something like that. They enter the cathode. The cations are reduced there, and the anions flow through the salt bridge back to the anode. You should have this memorized. Salt bridge, choice in a salt bridge is really important. Make sure you choose something that's going to be aqueous. Don't choose something that's going to form a precipitate, because if you do that, it's not going to be able to provide the positive and negative ions. So something like the NaNO3 is a good choice, because this is always soluble and so is nitrate. You can measure the voltage of a galvanic or a voltaic cell by finding what's called the potential difference. Now, there's 6 different names for potential difference, and they all mean the same thing. Potential difference is also known as the voltage, the electromotive force, the EMF, the cell potential, the cell voltage, the standard cell voltage, the standard EMF, the standard cell potential, the standard cell volts, the standard potential difference. When they put the word standard in front of there, they mean at 298 K, 25 degrees Celsius, 1 molar solutions, 1 atmosphere of pressure. Scientists have tabulated the standard reduction potential of a number of different things. This is also known as the standard reduction potentials table. It's right here. These things up here are very easily reduced. These things down here are very easily oxidized. The more positive it is, the more possible it is that it's going to be reduced. The more negative it is, the more possible that it won't be reduced, and the more possible that it will be oxidized. Know how to read this table. To calculate the EMF, or the standard electromotive force of a cell, also known as the voltage, also known as the cell potential, also known as the cell volts. I'm going to stress this. They use so many different ways of saying the exact same thing. To calculate that, you take the cathode minus the anode's standard reduction potential. We can see a calculation for this on page 864 of Brown-LeMay Burston. 864. Here's a redox reaction that we just used. Using the reduction potentials, calculate the standard EMF of the cell. Cathode, reduction. Anode, oxidation. Cathode is 1.33 volts. Anode, oxidation, 0.54. Find the difference, which is the subtraction, which is 0.79. Okay? Now, where would you find these standard reduction potentials? Well, you'd find them on the standard reduction potential table. They'll either give them to you on a table, or you'll have to look them up on here. You can use the standard reaction potentials to help you find out if there will be a reaction or not. If the volts are positive, yes, a reaction will occur. Here's an example. Tin and zinc nitrate makes tin, nitrate, and zinc. Write the half reactions. Tin goes to tin posi 2. Look, it's oxidized. It lost 2 electrons. The zinc went from Zn posi 2 plus 2 electrons to solid zinc. Okay? So which one was oxidized? This one. That means it's the anode. Which one was reduced? It's zinc. So reduced is the cathode. To find the voltage, take the cathode minus the anode. Well, my cathode right here, zinc, when I look it up, is right here, and it's negative 0.76. Negative 0.76 minus the anode. The anode is my tin. Now, I'm not going to find that reaction on here. I'm actually going to find the reduction half reaction. Tin plus 2 electron goes to tin. But that's okay. It's negative 0.14. Just put that number in. Negative 0.14. And I'm going to see here that negative 0.76 plus 0.14 is still going to end up being approximately negative 0.6, something like that. But it's a negative value. If it's a negative value, no reaction will occur. If it's a positive value, a reaction will occur. This leads us to, is a reaction spontaneous or not? E and G are related to each other. And remember, G tells us if a reaction is spontaneous or not. G, being negative, is spontaneous. G is equal to negative NFE. N is the number of moles of electrons transferred. F is the Faraday constant. And E is the EMF. If it's at standard conditions, we put little circles here, because that means it's at 25 degrees Celsius, 1 atmosphere of pressure. Remember units when you're working on this? A volt is a joule per coulomb. Volt is a joule per coulomb. I remember it as JVC. A Faraday is 96,500 coulombs per mole. Since a coulomb is equal to a joule per volt, you can put a joule per volt in there as well. And there's your units for that. You can use E to find G, or conversely, G to find E and E to find G, back and forth. What happens if we're in non-standard conditions? Well, remember, back in chapter 19, if G were at non-standard conditions, is equal to G circle plus RT natural log of K. Well, now what happens if we want to find E at non-standard conditions? Well, we just saw how G is equal to negative NFE. So really for non-standard conditions, this is NFE, non-standard. This is negative NFE standard conditions. Hey, could we find this and solve this for E non-standard? Sure we could. And assuming that we're at 298K, and the only thing that's changing is the concentrations, this now becomes E is equal to E circle minus 0.592 divided by N log of Q. This is known as the Nernst equation. The Nernst equation and the delta G is equal to negative NFE equations are given to us underneath oxidation-reduction electrochemistry right here. Okay? First of all, here is the Nernst equation in one form. E is equal to E cell minus RT divided by NF natural log of Q. But then when we're at 298, E is equal to 0.0952 divided by N times the log of Q. Okay? You can solve for the equilibrium constant by using this equation. Log K is Ne divided by 0.0592. And remember, underneath thermochemistry, over here where G is equal to negative NFE. So it relates E to G. Nernst equation problem is on page 874 in your text. Here's a Nernst equation problem where you're given a cell and they tell you that you're at non-standard conditions. Here's the standard voltage. And then you need to solve for Q. Q, remember, is products divided by reactants, the power of the coefficient. And in this one, you have to put concentrations and pressures in there at the same time because they're using a standard hydrogen electrode, or a hydrogen electrode anyway. And in this case, they solve for H+. Another example back here, one page before, found Q, found the voltage change. A couple of sample exercises from Brownlee-Burston. Check those out if you're stuck with your Nernst equation or didn't have great success with that before. What about electrolysis? This is the opposite of a galvanic or a voltaic cell. This is not where electrons are spontaneously created. This is making a non-spontaneous reaction happen by driving electrons into a cell. This is also known as an electrolytic cell, electrolysis, or an electrolytic cell. We put electrons into a substance to make them happen. Page 883 in Brownlee-Burston, 10th edition, got a great picture of this. Here is the electrolysis of molten NaCl. Molten, meaning melted NaCl. When it's melted, it forms Na pluses and Cl minuses. We have a voltage source where we drive electrons into it, and you'll notice electrons are gained by the Na plus. When they're gained, we say it's reduced, and so it's the cathode. Where the electrons go is the cathode in this case. At the anode, electrons are pulled away. And so the electrons are pulled away from the chlorine, and chlorine is oxidized to Cl2, from Cl negative to Cl2. So you can see that in this reaction, we have electrons being lost by the chlorine, electrons being gained by the sodium, And notice there's no salt bridge necessary here either, because we're simply driving electrons in there. And we can make some actual sodium, and we can make some actual chlorine. This happens with many molten metals as well. Definition of cathode and anode remains the same in an electrolytic cell. Remember, the cathode is where things are reduced, red cat. The anode is where oxidation occurs, anox. Quantitative aspects of electrolysis or an electrolytic cell. Two equations to remember. First of all, American Chemical Society. Coulombs, amperes, and seconds. An ampere is equal to a coulomb per second. Okay? Ampere is equal to a coulomb per second, or coulombs are equal to amperes times seconds. This is given on the yellow periodic table, but in a different form. Amperes in physics are symbolized by the letter I. Coulombs are an amount of charge symbolized by the letter Q. And instead of saying seconds, they put in T for time. It's right here underneath redox chemistry. I equals Q divided by T. If you forget what I, Q, and T are, they're listed over here. This equation and this equation are the same. Also remember that the Faraday is 96,500 coulombs per mole of electrons. Doing these problems, if you start with an amount of amperes, you got to get to coulombs, use moles of electrons, and you get to grams. If you start with an amount of grams, move to moles of electrons, which can lead you to coulombs, which eventually can allow you to use American Chemical Society to find the amperes. Here's an example problem. Calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten AlCl3 if the electrical current is 10 amps. 1 hour, 10 amps. We're given a time and an amperes. A time and an amperes. Time and an amperes. What could I find? Definitely could find coulombs. Once I find coulombs, use my moles of electrons, go to grams. Let's look at their results. Okay? Coulombs are equal to amperes times seconds. Amperes times the seconds gives me the coulombs. Next, go to moles of electrons. There's 96,500 coulombs in 1 mole of electrons. This is the Faraday constant, so multiply my coulombs by that. It's my number of moles of electrons. In this, you'll notice 3 moles of electrons are transferred to get 1 aluminum. So for every 0.373 moles of electrons, how many moles of aluminums will be created if 3 moles of electrons have to be transferred? 0.124 moles of electrons are created. 27 grams in a mole, 3.36 grams of aluminum are created. Qualitative aspects use this equation and the Faraday. Just to remember those two guys to be the link to get you to moles. And then once you get to moles, you can use the periodic table to convert. Let's look at some example problems from past AP exams. Here's 2006, question number 2. Answer the following questions about voltaic cells. Voltaic cell is set up using aluminum and tin. The half cells contain equal volumes of solutions that are at standard conditions. Write the balanced net ionic equation for the spontaneous redox reaction. Okay? Tin plus aluminum yields tin plus aluminum. Determine the value in volts, cathode minus anode. Cathode minus anode. Aluminum is the most easily oxidized, so you can see there it's oxidized in the equation. Tin is the most easily reduced, so you can see it has a more positive value. Calculate the value of the standard free energy change. G equals negative NFE. G equals negative NFE. 6 moles of electrons transferred. 96,500 coulombs. And here's my 1.52 volts. It's given in joules per mole or kilojoules per mole. How did I know there were 6 moles of electrons transferred? I've got to write a half reaction. Al goes to Al positive 3 plus 6 electrons, right? To balance that out. Go back to the basics and be able to write the half reactions. If the cell operates until it's 1 molar, 1.08 molar, and what is the tin concentration in the tin half cell? Nernst equation. Change tin concentration. 3 to 2. 0.12 moles of tin. Subtract, it went down to 0.88. In another cell, aluminum with tin half cells, tin is 0.01 molar, aluminum is 1 molar. Calculate the value in volts of the cell. Now plug that into the Nernst equation. 0.0592, 6 moles of electrons transferred. Here's my Q, products divided by reactances concentration, went to 1.6 volts, 1.46 volts. This was in 2006. Let's take a look at another one. 2009. Answer the following questions about electrochemical cells. Here's an electrochemical cell. Write the reduction, half reaction. Reduced. Ooh, which one's reduced? Okay. This is AGF. This is TLF. Okay. Got TL positives, TLs. Got AG positives. Got AGs. The voltage is 1.14 volts. Okay. AG positive goes to AG. The voltage reading is 1.14. Silver's half reaction on here is 0.8. Let's write that down. Write the reaction for the overall reaction. TL goes to TL plus 2. Silver's reduced to silver. Identify the anode in the cell, TL. In the diagram above, use arrows to indicate the direction of electron flow. Well, it goes from the anode to the cathode. Anode to the cathode. Anode to the cathode. Okay? Calculate the value of the standard reduction potential for the TL positive, TL half reaction. Remember, the EMF of the cell will equal cathode minus anode. This is why I had us look up silver. The anode we don't know. It's not on the standard reduction potentials page. But they do tell us the overall voltage is 1.14. 1.14. Now we can solve for the anode. Negative 0.34 volts. Standard reduction potential for this reaction is 1.2 volts. Assume that electrodes, salts, different electrochemical cells can be constructed to identify the two metals that when used to make an electrochemical cell would produce a cell with the largest voltage. Explain how you arrived at your answer. So here's a bunch of half reactions right here. Which one's going to be the largest? Two metal that leads to the largest E cell are the ones with the biggest difference. And so your biggest difference is going to be this positive 1.2 and this negative 0.25 right there. Predict whether platinum metal will react when placed in silver nitrate. Justify your answer. Now it is platinum plus AgNO3. Arrow, it'd be PtNO3 2 plus Ag solid. Put a 2 there, put a 2 there. Now, this would mean platinum would oxidize, and silver would go from Ag to Ag solid. Calculate E for this. If it's positive, it'll happen. If it's negative, it won't. Okay? This would be silver being reduced, 0.8. Okay? That means it would be the cathode. Minus platinum's, which is 1.2. 0.8 minus 1.2. Whoa, that's going to be negative 0.4. Negative 0.4. Because E for the reaction is negative, no reaction will occur. We just did one kind of like that as an example. Here's 2010, Form B. Bunch of half reactions. They give you a picture with a salt bridge. On the diagram, label the cathode. Okay? Most positive should be the cathode, right? Beaker on the right. So manganese or permanganate. Next, calculate the value. Cat minus An. E. Okay? 1.49 minus 0.77. 0.72 volts. Next, how many moles of electrons are transferred? 5. You'd have to multiply this one by 5 as well. So 5 moles of electrons are transferred. Backside, calculate the value of the equilibrium constant. Well, a couple of equations you can use, and one of the neatest ones is right here, where it just goes right from K NE divided by 0.592. Plunk and chunk into that equation, you get K equals 6.5 times 10 to the 60. You should anticipate getting a really big number. Really big numbers always happen in redox reactions that are have equilibrium constants. All of them have equilibrium constants, but they're really big. 3 solutions. Initial concentrations of the species are blop, blop, and blop. When the reaction mixtures come to each, which species will be in a higher concentration. You can read the answer to that because that's more of an equilibrium problem. Next, 2011, last year's electrochem question. If you're watching this in 2012, you might be watching it in 2020. It is not last year's anymore. Hydrogen gas, according to this equation below. Calculate the standard enthalpy change for the reaction represented by the equation above. Molar enthalpy of formation, blop. Okay? Products minus reactants. Notice the reactants are zeros, because remember the enthalpies of formation of pure elements in their standard states are 0. Next, calculate the amount of heat, Q. 10 grams converted to moles. 285 kilojoules are given off per mole H2. Where do they get that? Right here. Great thermodynamics start to the problem. You think it's all thermo, and then they ask one more thermal question before they drop the hammer. Vaporization is, what is the standard enthalpy for the reaction here? Notice how this reaction, okay, 2 reactions comboed, end up with a total. A fuel cell is an electrochemical cell that converts energy to stored fuel to electrical energy. A cell that uses H2 as a fuel can be constructed based on the following reactions. 2 half reactions. Now, it becomes an electrochem problem. Okay? We're at the overall cell reaction. So, cathode, anode. Take that one, look what they do to it. Okay? Make sure the electrons are equal. Got to double that one. Okay? And notice they reverse it. Okay? Add them together. There it is. 1 point. Next, calculate the standard reduction potential. Cathode minus anode, 1.23 volts. Next, assume that this much hydrogen is consumed after it operates for 6 seconds. Calculate the number of moles of electrons that pass through the cell. All right, you're going to go to moles to number of electrons. What's the constant that relates moles of electrons? Okay? 2 moles for every 1 gives you 1.9 moles. Now the average current in amperes. Okay? American Chemical Society. Coulombs in seconds. Okay? And 1.9 moles of electrons is 96,500 coulombs. That gives you the coulombs. Divide it by the seconds, and you now have the amperes. And they have one more question in there as well. Last question. That's it. That's it, folks. That's the end. My goodness, that's amazing. You'll notice there's electrochem questions just about every year. 2011, 2009, 2006, 2010. Leo the lion goes grr. Balance them. Know your steps for balancing the redox reaction. Know your Faraday. Know your American Chemical Society. Know standard conditions. Okay? Know the Nernst Equation at standard conditions. Know that Voltaic is also known as Galvanic. Know that potential difference has 16 different names. Voltage, EMF, electromotive force, electromotive cell potential, cell voltage, standard EMF, standard potential difference, standard cell potential, standard voltage. Know that EMF is cathode minus anode, and that you can find if there's going to be a reaction or not. G equals negative NFD. Good luck on your electrochemical review.